Hello everyone, welcome to the last lecture of our What is seminar. We are concluding this seminar with a special lecture with our beloved alumnus Balarka Sen from BMath 2021 batch, and he is currently pursuing his PhD under Professor Mohan Maharaj at the IFR Bombay. His current research interests are topology and geometry, and more specifically contact topology. And today he will be speaking about the Thurston-Bennequin inequality. Over to you, Balarka.
Thanks. Penkan's inequality. Yeah, so I'll just sort of say what the inequalities means and what is sort of the context around it. If you have any questions, feel free to stop me and ask at any point. Yeah, so this particular inequality was discovered by French mathematician Daniel Bencan somewhere around 1980s. So I'll tell you a little bit about it, but here's some organizational stuff first. So here's a sort of a graph of technicality versus time in the talk, where we'll start somewhere here because the topic is sort of unfamiliar and we don't know what the things that we're talking about are. But soon it will become familiar and it'll sort of drop down somewhere, and then hopefully it will stay quite easy for some time. And then if we go into the proof of Benkan's inequality, it'll sort of shoot back up. And I'm not sure if I'll get the time to cover that much, but in case that happens, just as a heads up. Nevertheless, the main takeaways I want you to have out of this is sort of threefold. And they are the first 3 points that I have written down here. One is, what is a contact structure? I think after this talk, everyone should sort of have a feel for what a contact structure is. And then, what is a Legendrian knot? And you should draw some explicit examples by hand of Legendrian knots. And then finally, some sort of familiarity to the point that we are not scared of Benkan's inequality, saying something extremely simple. Okay, so I begin with this intrigue. So I wonder how many of you have seen this picture before. This picture is a trefoil knot, the knot I have drawn in black. So it doesn't look like a trefoil knot, but it is one. The usual diagram of the trefoil knot is sort of threefold symmetry, has a sort of threefold symmetry to it. But this picture is the same knot as a trefoil knot. You can check that. And what I've drawn in red is sort of a oriented surface which bounds the trefoil knot. It's an oriented surface in R3. Like you get what I mean. And such a surface for a general knot is called a Seifert surface. So this picture is a Seifert surface for the trefoil knot. Okay. The exercise that I'll give you, to those of you who are interested in a sort of like cut and paste topology, is this surface in red is the same as a punctured torus with a disk removed. And that might not seem so obvious at a first glance, but that is what it is. And so the hint for how you would go about proving that is just compute Euler characteristic and see the number of boundary components. Those two invariants uniquely determine a compact surface with boundary. So in general, so in this case, what we have is a sort of Seifert surface of genus 1, right? Because it's a punctured, if you believe my exercise, it's a punctured torus. So it's genus 1. In general, you can ask, given a knot, what is the minimum genus Seifert surface it bounds? And remember, a Seifert surface is an oriented surface which bounds the knot. Okay, that's the kind of question that Benkan's inequality tries to answer. But before going there, I need to describe to you a bunch of players in this sort of story that is Benkan's inequality. And the first character is a contact structure. So what is a contact structure? Well, before going into the details of it, a contact structure is nothing but, I mean, when I think of a contact structure, I think of this picture. It is this picture. And what is this picture? It's a picture of a plane field, just like a vector field. But if you have a vector field, you have a vector at each point on your manifold, or let's say Euclidean space, if that's what you're familiar with. What I've drawn is a plane field. Instead of having a vector at each point, what you have is sort of an infinitesimal tiny plane at each point, a tangent plane, if you will. And these are the planes. A contact distribution is a particular kind of plane field which has the property that it twists too much. And what that criterion, twisting too much, means can be explicated in a mathematical format as follows. Um, One says that the contact distribution is nowhere integrable. So by the way, my notation for the contact distribution is xi, and the plane, so it's a collection of planes xi p, where p varies over the real space, 3 space. And I'm only going to stick to the 3 space, although much of the story generalizes to 3 manifolds or even high dimensional manifolds, but I'm going to stick to R3, 3 space. And the distribution is called nowhere integrable, or the plane field is called nowhere integrable, if at no point on the 3 space can you draw a little patch of a surface such that all the planes at each point of that surface are tangent to the surface. So it's sort of a polar opposite to a vector field in some way, because vector field you can always draw sort of integral curve through each point. But for a contact distribution, you cannot draw an integral surface. Does that make sense? If you have any questions, you can ask. That's what a contact structure is. Is the definition completely clear?
Yeah.
Okay, thanks. So next, I define what Legendrian curves are. Yeah. So we saw what a contact structure is. One way to think about a contact structure is, so how do you think of a vector field? A vector field is sort of a force field. Think of rowing down a boat, rowing down a river in a boat, and sort of the current of the river is sort of forcing you to go in a particular direction. The integral curves. The way I would like to think of a contact structure is, you are flying in the 3 space in an aeroplane, and because of the wind in the 3 space or some unforeseen mechanical constraints of the plane, of the aeroplane that you're in, you are sort of forced to stay tangential to the planes at each point. Okay? So the trajectories of this aeroplane are necessarily tangential to each point of these planes. Right? And so what will the trajectories be? The trajectories that you'll get are called Legendrian curves. The definition is, you have a curve in R3 and a contact structure xi in R3. You say it's a Legendrian curve if the derivative of the curve lies on the contact plane passing through that point at the time, and each time, for it's true for each time. Is that definition clear? Are there any questions I'd like to ask?
It's fine.
Okay, cool. So I give now examples of contact structures. So this is where things get a little bit more technical. You need to know what a one form is. Okay. If you know what a one form is, you can follow this slide. A contact structure, you can draw, of course, you can draw a plane field, but that's not always possible, and sometimes drawings can be deceiving. So what you can do is you can write down the contact plane field or the contact distribution explicitly in terms of a one form. More specifically, as a kernel of a one form. A one form is nothing but a linear function at each point on your manifold, in this case R3. And so consider, for instance, dz minus y dx. That's a one form. That's a linear function at each point of R3. And you look at the kernel of it. It's a linear function and it's non-zero, so the kernel will be a 2-dimensional subspace. So that's one way you'll get a field, right? A plane field throughout your space. And my claim is the picture I showed you earlier is just kernel of this particular one form, dz minus y dx. And that's easy to see because just think of it in naive terms. Dz minus y dx equal to 0, that's the kernel, implies that y equal to dz by dx, which means that the zx slope of the plane should be equal to the y coordinate that the plane is situated at. And that's exactly why you see this twisting behavior, the plane's rotating like a turbine. In general, any plane distribution which is smooth can be described as kernel of a one form. But the real question is, when is it a contact structure? That is to say, when is it nowhere integrable? And that is answered by Frobenius integrability theorem, a very old theorem, which states that if xi equal to kernel of alpha is nowhere integrable, then alpha wedge d alpha is not equal to 0 everywhere, and vice versa. So for instance, you can using this, you can construct or conjure new contact structures if you like. The old one, the one I showed you, I would call xi naught. It's called the standard contact structure in R3. And this one I'm drawing here, I'll call xi1. It's kernel of this one form, where r, z, r, theta are cylindrical coordinates on R3. And it looks something like this. It's z invariant. If you translate z going to z plus c for some constant c, that's invariant under that. And it's radially symmetric. So if you rotate along the z-axis, you get a completely symmetric picture. And the planes sort of twist more than the earlier picture, xi naught. And if you see, starting at the origin, it's completely flat, and it goes all the way up to the boundary and twists a whole turn. While this never does that. The previous one never does that. It just goes off to infinity and never twists completely. But this goes through a whole turn, complete twist. And it's also nowhere integrable, which you'd expect because it's so twisty. Okay, so I told you what contact structures are, I gave you some examples. I told you what Legendrian knot is. How do you draw Legendrian knots? Here's one way. So start with the old contact structure, the standard contact structure, xi naught. I'll only focus on xi naught for some time. So here's a natural way to sort of generate aeroplane trajectories which are extremely knotted, but are still tangent to the plane fields anyhow. What you do is you draw in the zx plane, you look at the zx plane, and you draw any sort of random knot diagram or sort of any random curve which is sort of sufficiently generic enough. It doesn't matter. And you solve for y equal to dz by dx. Now you know z and x completely because you've drawn it on the zx plane, a curve, zt comma xt. So what is y, where y equal to dz by dx? You solve for that. And then automatically that satisfies the property, right? Because along the curve, dz minus y dx is 0 because I have literally solved for y equal to dz by dx. So I have drawn a Legendrian knot. Have I? There's a problem. The problem is the following. At points where the curve is vertical, so tangent vector to the curve points this way, vertical, I have dx equal to 0. So I get some expression like 1 over 0, right? Dividing by 0. So I cannot solve for y. But there's an easy way to remedy that. What you have to do is you have to cusp out these points of vertical tangencies. And by a cusp, I mean the following picture. This model is called a semi-cubical cusp. It's xt equal to t square and zt equal to t cube. So if I replace each vertical singularity by that, then I have something nice, because if I now plug in zt equal to t cube and xt equal to t square in the expression for y that I'm solving for, I get 3t square times dt by 2t times dt, and dt cancels, t cancels with one of the t's up here, so I get 3 by 2t. And that is a perfectly valid quantity, right? It's a well-defined quantity. Do you agree?
Yeah, but aren't when we introduce the cusp, aren't we getting some kind of non-smooth point?
Yes, it's a
Like
non-smooth point in the zx projection. But when you lift it back up to the 3 space, it's no longer non-smooth. So let me convince you.
I see. Right.
So have you ever tried this following experiment with your headphone wires? You twist your wire up like this, and you're seeing top down. It looks something like this. But then when you see from the side, it looks like a cusp. So some projection
Right.
is, yeah. So that's what's happening. The lift is completely smooth. You can check that. So as a corollary of this, you can check that any knot can be drawn as a Legendrian knot, because you can literally draw a knot diagram downstairs on the zx plane and then lift it back up by putting some number of cusps wherever there are vertical singularities. You have to be a little careful at the crossings, but modulo that care, you've basically drawn any knot as a Legendrian knot. Okay. So now that I've told you about Legendrian knots, I have to tell you about, okay, so how should I put it? Right. So even though any knot can be drawn as a Legendrian knot, the theory of Legendrian knots is quite different from the theory of topological knots, smooth knots. The reason is that what is the sort of equivalence that you generally speak of when you speak of knot equivalence? If you have one knot, another knot, we say they are equivalent if there's a smooth isotopy between them through knots, right? Through smoothly embedded knots. And you would like to have a similar equivalence relation for Legendrian knots, where two Legendrian knots are equivalent if they're connected by two Legendrian knots, by a family of Legendrian knots, smooth isotopy of Legendrian knots. So that's where the difference comes in, because even though one knot can have a Legendrian representative, it can have inequivalent Legendrian representatives. So you can realize a single knot which has two different Legendrian knots which are not connected by Legendrian isotopies. And how do you distinguish two Legendrian knots up to Legendrian isotopy? That's where these following invariants come in. These are not invariants for Legendrian knots, and these distinguish if two Legendrian knots are the same or not. One is a Thurston-Bennequin number. It's quite natural if you sort of follow my analogies. Think of along the, what is a knot? The knot is the aeroplane moving in the three space, following by being tangent to the plane fields everywhere, right? You just go through the whole trajectory, do a full loop along the trajectory in your aeroplane, and see how many times the plane field twists along the trajectory. The contact plane field twists, right? That's the definitional property of the contact plane field. It has to twist. So how many times does it twist? Full 360-degree twist as you go around the knot. That number is called Thurston-Bennequin number. There's a catch. The catch is that what does twist mean? It has to be in reference to something. You have to say something is zero twist, right? That's clear if you have an unknot. If you have an unknot, obviously the horizontal plane distribution is the zero twist. It doesn't twist anything, no twists. But what if you have a more complicated knot, like let's say the trefoil? What does zero twist mean? You have to fix that. You have to fix a zero. But once you fix a zero, this number makes sense. It's like instead of a vector, you have an affine vector. But once you fix a zero, it's perfectly fine. Does that make sense?
Yeah.
Okay, cool. Here is another invariant, and it's slightly harder to describe. It's called a rotation number. Earlier we saw Thurston-Bennequin number is twist of the tangent planes as you go around the knot. How many times the tangent plane itself twists. The rotation number is how many times the tangent vector to the knot twists inside the planes. Okay, so let me describe it. Here is an example. I have a black knot, part of a knot, it's an arc. As tangential, and it's Legendrian, it's tangential to the planes at every point. So as I go around it, I observe that, okay, so I orient the knot, okay, so I have a particular orientation of the knot, and then I look at its tangent vectors. The tangent vectors are contained in the planes at every instance of time. And then if I sort of identify all the planes with a single plane, these are all copies of R2, right? So they're literally just one copy of R2, positioned in different ways. And then I plot the tangent vectors on this one single copy of R2. I get the same vector every time. It's constant. There's no sort of weird stuff happening. Nevertheless, you can do a small modification of this knot, which is what I've drawn in the blue curve. It's the following. Let me try to describe it verbally. I move in the same general direction as the black knot, but then I sort of slide off this slanted plane and then sort of pick my pace back up and go to the end point of the black knot. Is the description of the blue knot clear? I have just sort of went and then sort of slid off in the slippery slope that is this middle plane. And then I've picked my pace back up and went all the way up there. So I've just done some loopy there. Is it clear?
So, I mean, maybe this is sort of a vague question, but like here in the current example, all the three planes sort of like you've shown aren't really twisting, right? So here, the thing that you're saying is a little clear, is somewhat more clear. That okay, we can make a choice and sort of slide off and pick up pace again. But what if the middle thing twisted somewhat more? So how do we decide to sort of slide off in the direction of the twist or something like that?
I understand. I understand your question. So the point is that exact twist doesn't matter. The point is that it has to twist. Going from here to
Right,
here, there has to be some amount of twist because it's a contact distribution. It is nowhere integrable. There has to be some amount of twist.
right.
And because of this, we can slide off at any time. Sort of any time I can slide off and then pick my pace back up and go. Okay.
I see.
Okay. So choose a, this is a non-canonical choice, but that's okay. So do that. And then you see the tangent vectors to the blue curve, they rotate. More precisely, if I plotted the tangent vectors in this single R2 that I canonically identified with each of them, canonically, quote unquote, then I get that the tangent vectors to the blue curve rotate once because of this twisty here. And that is the notion of rotation number. If you have a Legendrian knot in a contact structure in 3 space, then the rotation number is the number of times the tangent vectors to the Legendrian knot rotates by 360 within the contact planes. Now, again, there is a choice, is what is 0, or it's not exactly what is 0, but here the choice is that of identification of the contact planes with a single R2. There might be many non-canonical ways of doing it, but you have to fix one. And if you fix one, then this is well defined. Okay, so those are the other two invariants. If you have any questions, feel free to ask. Thurston-Bennequin number, rotation number. Okay, so I'll move on. Maybe I'll come back to this slide sometime soon. Okay, so let me just state Bennequin's inequality. We have all the data we need. The inequality says the following. Suppose you have a Legendrian knot in R3 3 space, and you have the standard contact structure. This is important. Okay, so maybe I'll do a red box around it. It's not true for any contact structure. It's true for the standard one. For the standard contact structure, suppose I have a Legendrian knot. That is to say, an aeroplane trajectory where the aeroplane is following the constraint given imposed upon by the standard contact structure. Then the following inequality holds. The Thurston-Bennequin number of the Legendrian knot plus the modulus of the rotation number of the Legendrian knot is at most negative of the Euler characteristic of any Seifert surface that our knot bounds. It's a smooth knot after all. It bounds a Seifert surface and can potentially bound many Seifert surfaces to the minimum genus one, because that will maximize the Euler characteristic. That's because Euler characteristic is 2 minus 2g. G is minimized, then pi is maximized. So, and this inequality is true. Okay, so this side is contact topology. I'm telling you something about smooth topology of the knot. Is the statement of Bennequin's inequality clear?
Yeah.
Okay. Let me do one application. So I have two applications written down. I'll do application 2 first. Okay. Simple application. The theorem, this is originally what Bennequin's inequality, what Bennequin discovered Bennequin's inequality for. It is to distinguish the standard contact structure and the one I showed you before. Remember this disk, the radially symmetric one. So this one is called the standard contact structure, and this one is what is known as an over-twisted contact structure. The name is self-explanatory, I think. It twists too much, I explained before. These are not quote-unquote equivalent. An equivalent in the category of contact distributions, which means that okay, so I'll explicate that notion. Two contact structures are called contactomorphic if there is a reparametrization of the free space that you can make so that the plane fields here become plane fields there. Okay, that is to say there is a diffeomorphism of R3 to R3 such that if you pull back the plane fields here, you get the plane fields there. These two contact structures are not equivalent up to such reparametrization. That is to say they are not contactomorphic. And the way you prove it is as follows. You have to use the Thurston-Bennequin number, rotation number, R invariance. Observe in Xi1, in this weird rotationally symmetric contact structure, there is a knot which has rotation, which has Thurston-Bennequin number 0. And this is the following knot. You just look at the boundary of this disk. That's a Legendrian knot, right? Because the boundary of the disk tangent vectors are contained in the plane fields at every point, right? That's a Legendrian knot. What is Thurston-Bennequin number? It's 0. I mean, come on, because the planes are absolutely horizontal along the knot. This is Thurston-Bennequin number 0. And it has a ciphered surface, which is a disk, because it bounds the disk. It's literally the unknot. So all the characteristic of the ciphered surface is, all the characteristic of the disk, which is 1. So if they were contactomorphic, if xi1 and xi0 were really the same, the Thurston-Bennequin inequality, or the Bentham inequality, I'm sorry, it's also called Thurston-Bennequin inequality because of related work that Thurston did. That would also apply to xi1, right? Because they are sort of the same contact structure. So if it's true here, it should be true here. But assuming it's true here, we would have Thurston-Bennequin number of lambda, which is 0, plus modulus of the rotation number, which is something positive, is less or equal to negative the Euler characteristic of this disk, which is -1. That's a contradiction. Positive number cannot be less or equal to -1. So you know that these two contact structures are different, truly different. So let me now do application 1, and for that I need to go back a couple slides. This slide I missed, I'll sort of fill it in. I told you what Thurston-Bennequin number and rotation number are, but I haven't told you how to compute them. So now we can pretty much draw any sort of, we can draw lots of Legendrian knots. We just draw some type of a knot diagram in ZX. By the way, this diagram is called the wavefront diagram of a knot. And the reason that it's called that, it's popularized by Arnold. And it's called that because it has deep connections to optics. But anyway, when you think of sort of like your, in your sort of coffee mug, you can see this catenoid if light reflects on it. And that's reminiscent of this kind of cusps. But that's all I'm going to say about that. It's a deep connection. So let's draw some Legendrian knot by drawing its front diagram, wavefront diagram. I have drawn, so you can check this trefoil here. So how do I compute Thurston-Bennequin and the rotation number given this knot diagram? And there are very simple formulas for it that you can compute. For this, I need to tell you two things. One is the story of undercrossings and overcrossings. When you draw knot diagrams in smooth topology, you always have to sort of specify which one is crossing which one. In contact topology, you don't have to do that. It's very easy because the y coordinate is dz by dx, which is a slope, right? It's a slope in the zx projection. And at this point, the slopes are different. So one is automatically overcrossing, one is automatically undercrossing. In fact, you can check that because I have drawn zx, the y-axis is sort of pointing that way because of the, whatever we call it, the right-hand rule, x cross y equal to z. So which means that this, the y-axis, part of the y-axis coming out of the plane of the paper is -y, in fact. Which means that the crossing, at the crossing, the strand which has more negative slope is the overcrossing strand. So this is overcrossing, this is overcrossing, this is overcrossing. Okay. That's one thing. Crossing is done. I need to tell you about the sign of a crossing. So this is a notion in smooth knot theory. If you have a crossing with the knot oriented, so then the crossing, that this pair of strands has some orientation. And you can check if an orientation is compatible with the right-hand rule or not by sort of putting your, so let's just look at this picture. Putting your right thumb over this strand, pointing in the same direction as the direction marked here, and then folding your right palm and see which way it folds. In this case, we see that it in fact sort of folds this way, which means that this is a positive crossing. You call that's the positive crossing. You say that's positive. And if it's the other way around, I mean, if the direction is reversed, you call it negative crossing. The ride of a knot or a knot diagram is the sum over all these numbers, +1, -1, +1, -1 over all crossings. That's called the ride. You can check that the Thurston-Bennequin number and the rotation number are simply given by the following formulas. Thurston-Bennequin number is ride of the wavefront diagram that you drew minus half times the number of cusps. And the rotation number is half times the number of up cusps minus the number of down cusps. And up and down just means you orient the knot, and then you see if the orientation is going up in the z direction as you traverse the knot and across and sort of traverse the cusp. This is up because it's pointing up. This is down. Well, I don't know. This is down because it's pointing down. So let's try and compute for this particular wavefront diagram what's happening. The Thurston-Bennequin number of this is ride. So what is the ride? There are 3 crossings, 1, 2, 3. And you can check that this is the overcrossing guy because it's negative slope. And this is the undercrossing guy, and it's +1. And all the other ones are +1. I think it's called the right-handed trefoil. There are 3 crossings. Everything is +1. The ride is 3. And you subtract half times the number of cusps, of which there are 4. So the final answer is 1. Thurston-Bennequin number is 1. And the rotation number will compute. This is up, this is down, this is up, this is down. So we have 2 downs and 2 ups. So 2 minus 2 equal to 0. That's the rotation. Okay. Is that clear? Has everyone understood what this is?
Yeah.
Okay, perfect. So now I go back to application 1. It's a simple application. The trefoil knot is not an unknot. So suppose it was. So this is a purely topological theorem, right? The trefoil knot is not an unknot. I claim is that it follows from contact topology. By doing this extremely complicated sort of plane field, blah, 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 you can derive a topological result. So if it was, it would bound a disk. And then you use Thurston-Bennequin inequality. Thurston-Bennequin number plus mod of the rotation number is supposed to be less or equal to minus of the Euler characteristic of the Seifert surface, in which case that's a disk, so it's -1. But the Thurston-Bennequin number we computed, it's 1, and rotation number we computed 0 for this particular trefoil. So 1 is less or equal to -1, contradiction. So trefoil knot is unknown. Okay, so that's pretty much what I would like to sort of say without going into next slides are proofs and more ambitious applications. Okay, so let me just go back to this organization slide. So optional, as I've written, is the proof, and extremely optional is a particularly ambitious application, which I definitely won't have time to say. So I don't know how much time I have. So maybe one of you can point out how much time I have, or I would like to take questions. If you have questions, that's fantastic. Let's discuss the basics. I have 20 minutes. Okay. 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 So okay, let's just okay. Any questions? Yes, please ask questions.
Yeah, so I had one question. So like the Thurston-Bennequin number
Yeah.
is like a little bit easier to believe that okay, that is indeed invariant. So is there some intuition behind why the rotation number should be invariant? Because it seems like we are making a lot of choices.
That's a very good question. Yes. Well, there's a hack proof of this, which is essentially you can cook up, the Reidemeister moves, right? In smooth knot theory, you can cook up similar moves called the Legendrian Reidemeister moves, and then you can see the rotation number is invariant under those moves, and then you're done. But that's a hack proof. It's not an insightful proof. What is really insightful is for me is that thinking about, I don't know. So thinking about a contact structure as sort of a area form, except on these planes. It's an alpha is a 1 form, right? It's not a 2 form, but d alpha is an area form. And what you have is d alpha on these planes. These are area forms. And once you have a sense of area, you can always sort of integrate stuff, right? D alpha, you integrate stuff, okay, and you get invariance out of it because Stokes theorem. So what you can do here is do something similar. You take any knot. Any knot has a ciphered surface in R3. That's true. You take the ciphered surface, and then this contact plane fields is something we call a bundle. It's a rank 2 bundle on the ciphered surface. Okay. It's a trivial bundle, but it's a bundle. And the fact that it's Legendrian gives you a section of this bundle on the boundary. So you have a section of the bundle, and then you can compute, because you have a sort of a area form on each fiber. You can compute the so-called first churn class of this bundle, the relative churn class, and that's exactly what the rotation number turns out to be. So it's a high-level explanation, but that's much more insightful for me than just a hack computation. I don't know how much of that made sense, but hopefully I can convey something, because sort of you have this d alpha and you have this ciphered surface. You choose two different ciphered surfaces, and this rotation number, my claim is given by integrating some quantity d alpha over something, and then of course the choice of the ciphered surface doesn't matter, because d alpha, it doesn't, only the boundary matters because of the Stokes theorem. So hopefully that I can convey some of the intuition behind why rotation number is an invariant. Does that make sense? Or vaguely?
Yeah.
Okay.
That makes a lot of sense actually.
Okay. Yeah. Cool. Okay. So I will. If you have any questions, you can ask. Meanwhile, let's see. Okay. So let me take a sort of a vote. Do you want to see the proof, or do you want to see the ambitious applications? So just to be clear, my ambitious application is a construction of an exotic R4. An exotic R4 is a manifold which is homeomorphic to R4, smooth manifold, but not diffeomorphic to R4. Do you want to see the proof or the ambitious application?
Yeah, go towards the application.
Okay. So anyone else that would like to vote otherwise? Okay. Okay. So let's do the application maybe. Okay. Okay. So let me. It's not a straightforward application. There are many hard steps involved, but hopefully I can convey each step. So the first thing is that the Benkan's inequality has a very intriguing generalization to what is known as a slice Benkan inequality. So for that, I need to describe to you what a slice knot is. The idea is something like this. If you have a knot in S3, the ciphered surface is surface the knot bounds inside S3, right? Right. But instead, you can think about surfaces that the knot bounds inside D4, because boundary of D4 is S3. And you have the knot here. Okay, some complicated knot. That's not an ideal picture, but this is a knot in S3, and it will bound some. It might bound some stuff here, right, in D4. I mean, it will, because it's now homologous and so on. Then, yeah. And that surface, you can sort of minimize the genus over that surface. Instead of minimizing the genus of the ciphered surface, you can push it. You can look at surface bounded inside the 4-ball, not just in S3, and you can minimize genus there. And that genus might potentially be less than the genus of the knot, right? It's less than the genus of the smallest genus ciphered surface, potentially. That's called the slice genus. Okay. So, and a knot is called smoothly slice if it has slice genus 0. Let me give you an example. Example is here. I have this complicated knot drawn here. Okay. This knot I claim is a slice knot, even though it's not an unknot. You can check it's not an unknot. It is a slice knot. How to see that it's a slice knot? Consider this surface that I've drawn here. It's a self-intersecting surface. It's not a ciphered surface. It intersects itself on this arc and on this arc. Then imagine coloring the surface so that at the intersection where two pieces of the surface hits each other, one surface is red and another is blue. So here I should have drawn a little red here. I don't have to. It doesn't have to be uniform coloring. It can be a color gradient. That's fine. Same color, putting different color gradients. So it's red here, and then the hue goes down and becomes blue, maybe. Okay, I should have drawn that, but I didn't draw it. I was too lazy. Now what you have is a self-intersecting surface in S3, but with a color gradient. And if you add that color gradient as as an extra coordinate, fourth coordinate, now the surfaces no longer intersect. They now live in D4. They live in R4 certainly, because I have added this extra color coordinate, and they no longer intersect because at the points of intersection, the two pieces of the surface have different colors. One has red, one has blue. So they're different because even though first three coordinates match, the last coordinate doesn't. It's the color coordinate. So this surface, I have sort of pushed this surface inside D4 by choosing a sort of color gradient on it. And what I've produced is a disk, because if I sort of imagine that the self-intersections aren't there, and that's what's happening in the fourth dimension anyway, then it's just a disk. It's just a disk. You just follow it along, you see it's just a disk. Disk wrapping around itself in a weird way. So this is a slice knot. Is this example clear? Clear, unclear?
Yeah, I think it's cool.
Okay, perfect. Okay, so that's a slice knot. What the slice-Bennequin inequality says is the following. Suppose you have, again, standard contact structure on R3, a Legendrian knot. Thurston-Bennequin number plus mod of rotation number is less or equal to not just the Euler characteristic of any minus of Euler characteristic of any Seifert surface, but minus of Euler characteristic of any smooth embedded surface in D4 which bounds the knot, which I have written like this: 2GS minus 1. 2G minus 2 is negative Euler characteristic for a closed surface, but there's a puncture because it's not, it bounds. That's a puncture. So I have to subtract 1. So 2GS minus 1. GS being the slice genus. So I should have written that slice genus. That's the statement of Thurston-Bennequin inequality. It works, the slice-Bennequin inequality. It works not only for Seifert surfaces, but also for the surfaces which the knot bounds inside D4. Smooth ones though. Okay. That's the statement. Okay, so now I'll talk about a little bit about topological sliceness. So there's whenever you go to dimension 4, there's a strange thing that occurs. Smooth is no longer the same thing as homomorphic. I mean, diffeomorphic is not the same thing as homomorphic. Smooth embedding is not the same thing as topological embedding. So what is strange is that there is a separate notion of sliceness called topological sliceness. We have discussed smoothly slice. There's a notion of topological sliceness, which is that the knot bounds a topologically embedded disk in D4. Topologically, yeah, it's not smoothly embedded, topologically embedded disk in D4, which is still nice enough in the sense that it's locally flat. What locally flat means is that it's a submanifold such that locally it looks like R2 in R4, but up to homomorphism. You can change coordinates by a homomorphism so that it looks like a flat plane R2, but not by diffeomorphism. Not necessarily by diffeomorphism. That's what a locally flat disk is. And how I imagine a locally flat disk is you have this knot here, and then this disk is maybe some graph of some crazy function. And no way you can smooth it. Right? No way you can change coordinates so it looks like a smooth graph. So that's sort of my cartoon of a locally flat disk. In reality, they're much more complicated. And what Friedman proved in I think late 80s, as part of his solution to the four-dimensional topological Poincare conjecture, for which he eventually got the Fields Medal, was there are knots which are topologically sliced but not smoothly sliced. And in fact, knots which have Alexander polynomial 1 are topologically sliced, always. Alexander polynomial is an invariant of a knot. I won't define it here, but you can look that up. There's a nice kind relation you can use to compute explicitly for some examples. And here is my exercise for you. Suppose you take the trefoil knot, and you take 2 copies of the trefoil knot and sort of link it like this little linkage I've drawn here at a point, while potentially allowing some number of twists. This object is called the whitehead double of a knot. Given any knot, you can take the whitehead double. You take the same knot, double it, take this knot and another copy of it, a copy of the knot, and sort of braid the two together somewhere. And then at a point, you sort of erase a little part of the arc and then sort of link them like this, like a half link at that point. This is a whitehead double of a of the trefoil, and my exercise for you is to look up what Alexander polynomial is, just the sign relation definition of it, and check that the Alexander polynomial of the whitehead double is always one, no matter what knot, no matter how many twists you put, it's always one. So these are topologically sliced. It's a hard theorem. It's a hard theorem that this is true. I mean, Friedman got the Fields Medal for it, but it is a fact. I will like to show you that some whitehead doubles are not smoothly sliced, and that you can prove using slice-Bennequin inequality. So here is my attempt at drawing a Legendrian whitehead double. I have picked you can see here, I have chosen the Legendrian knot diagram of trefoil, and I've taken a slight copy of it, double of it, by just pushing it in the z direction a little bit. It's this guy over here, and then I sort of, without putting any braids, I just sort of interlink it, and this operation exactly corresponds to um, putting the links together, because at this point it'll overcross, at this point it'll undercross, well, other way around. This is what the picture looks like when you lift it up in 3D, because of the fact that slopes are uniquely determined. Y coordinate is uniquely determined. It's a slope. You can check that this object has Thurston-Bennequin number 1, but rotation number 0. Okay. And why is that true? Well, you can check. The ride you can compute. Okay, I'm not doing it right now, but there are 1, 2, 3, 4, 5, 6, 7, 8 cusps, and ride comes out to be 5. Yeah, you can check that. Just check that. So this is a mini exercise for you. Orient the knot, compute the ride, and then compute Thurston-Bennequin number. Turns out to be 1. And the rotation number is 0. That's fairly easy to see. You again see that every time you encounter up cusp, it cancels the down cusp. Here you see up, but then down, and goes on. But just because you have a double of it, and the double is traversing the other way. If it's going this way, and the double is traversing the other way. So this particular knot has TB equal to 1 and rot equal to 0, which means that if it bounded a smooth disk, if it was smoothly sliced, it would satisfy the inequality 1 plus 0 is less or equal to minus 1, because that's the Euler characteristic of the disk, negative of it, which is impossible. So it's not smoothly sliced. Okay. So using this, you can construct an exotic R4. The construction is as follows. Suppose you have a manifold which is sorry, that's the theorem. Theorem is that there is a smooth manifold such that M is homeomorphic to R4, but M is not diffeomorphic to R4. And the way it goes is, pick a topologically sliced knot which is not smoothly sliced, like the example earlier I gave you, whitehead double of the trefoil knot. Then consider S4. You have to think in 4 dimensions now. I'm sorry about that. Take S4 and take the equator, that's S3. On S3, you have the knot, which I have drawn as 2 dots because of my number of dimensions is too low. It's actually an S1 inside S3. That's the knot, that whitehead double knot that I wrote earlier. It's because the Alexander polynomial is 1. That's an exercise. There exists a locally flat disk. It bounds on either side because both sides are D4. This is D4. This is D4. It bounds one such disk. Okay. So what you do is sort of take a little neighborhood of this disk and erase it. Just take a little neighborhood and drill it out. Just delete it. Delete the little neighborhood out. From which side? From this side. That has the effect that on the other side, what you're doing is you're just adding that little piece back in. Right? So now what you have is a new decomposition of S4 consisting of this piece and that piece. Okay. Clear? The construction is clear? The carving out construction?
Yeah, sure.
Okay. Okay, so then what I will do is I will delete this point, the north pole of S4. I delete this point. Then what I get is that I'll look at the two pieces. I have one bottom piece and one top piece. The top piece has this point deleted. It's a non-compact manifold. And now there's a theorem of Quinn, again a hard theorem, which says that all non-compact connected four manifolds admits a smooth structure. It's not obvious that this is true. I mean, you probably haven't seen an example of a topological four manifold which is not smooth in the night sky, but these things exist, so one has to sort of check. For those who don't care, it's a technical result, but these kind of things one has to be extremely careful about in 4 dimensions. So this is actually a smooth manifold. I mean, it doesn't look smooth, right? Because we have deleted a neighborhood of a topologically embedded, locally flat disk. Why on earth should this be smooth? Doesn't make any sense. But it is smooth. That is to say, it admits a smooth structure. And if you sort of smoothen it out, this part becomes very nice and smooth. But the smooth structure, or the atlas at infinity, sort of goes extremely wild, in the sense that the smooth structure cannot be compactified by adding this point back in. That's the point of deleting this point. That's the reason, the raison d'etre behind deleting this point. If I had this point, I would not be able to smooth it. It's because of this non-compactness that's smoothable. That's the theorem of Quinn. Okay. So now I have this nice smooth piece. What I will do, I'll just glue so here's what's going on. I'll just glue this smooth piece to the bottom piece downstairs that I had here. In this, I have the top piece. Maybe I'll roll it top. This is the top piece, and this is the bottom piece. This is also the top piece. Right? Top piece has two disconnect components in my picture, but it's not disconnected because this disk is two-dimensional. If you throw a two-dimensional thing out of a four-dimensional object, it's connected. Exercise. So I'll glue the top piece to the bottom piece, but then the bottom piece is also weird, right? You have this locally flat disk, and you glue a little neighborhood of it. Why is it smooth? It is smooth because this piece, this little neighborhood, is just d2 cross d2. So what you should think about is there's a nice smooth model for it, which is this bottom piece that's just d4, and then you add a d2 cross d2 to along this knot. The knot lies on this S3 boundary of D4. This is D4. This is S3. The knot lies along this. It's an S1. You look at a tubular neighborhood of this knot. It's a smooth knot. Tubular neighborhood exists. That's S1 cross D2. And then you glue in a D2 cross D2 to S1 cross D2 by sending the boundary of D2 to the knot. That's what this gluing operation is. And this is a nice smooth manifold because I have all the gluings are smooth. And this is clearly homeomorphic to this. But then this has a smooth structure. By this homeomorphism, pull back the smooth structure here and then make it smooth. Okay. So now I have a nice smooth piece, which is the top, smoothened top, smoothened, and I have the bottom. Top is an extremely bad notation because I'm talking about topological and topological different of the diff category in the top category. So I'll just say the top part smoothened and the bottom part smoothened. So I just glue them because the boundaries look the same. They're the same. Glue them back. So I glue them back. I get some manifold like this. This manifold is homeomorphic to R4. Why? Because essentially I've done nothing but delete this point, right? Topologically, I've just nothing but delete this point, and the rest was playing around with the smooth structure here and here. So it's just S4 minus a point. It's R4 topologically, but the smooth structure is extremely different. Why? Suppose it was the same smooth structure as R4. Then this bottom piece with D2 cross D2 glued along this knot, this would admit a diffeomorphic embedding in S4, right? Because if this was standard, then it can be compactified. If this is just standard R4 with a S4 with a point removed, smooth structure, then it's just a subspace of S4. So it compactifies to a smooth structure on S4. So the entire thing can be done on S4 without removing this point. That's the point. If it was diffeomorphic to R4, the entire thing can be done without removing the point anyway. So then this bottom piece would admit a diffeomorphic embedding in S4, which would mean this knot bounds this disk, which is point cross D2, and that's a smooth disk. So it'd be smoothly sliced. That's impossible. We just demonstrated that. the knot we came up with is something which is topologically sliced but not smoothly sliced. Contradiction. This manifold is an exotic art form. That's my um, example. Ambitious application, if you will. So thanks. That's it. If you have any questions, feel free to ask.
Any questions?
So basically, in the proof of that it is not diffeomorphic to R4, and along with the Benquin equality, the key part is the Quine's theorem. That
Exactly. Yes.
because the compactification part is the point where we are getting the diffeomorphism into a space.
Precisely. That's the key part. There are a bunch of hard theorems going inside this proof, which is one is slice Benka inequality. That's a hard theorem. That there I know of no easy proof of it. Sort of all proofs that involve Kronheimer-Markov floor theory, gauge theory. But at least it's understandable because it's it's sort of a spiritual successor to the Thurston-Bennequin inequality. The second one is Friedman's theorem, which is there exists these. I mean, any Alexander polynomial one knot is topologically sliced. That's not clear at all. And the third thing is this theorem of Quine, which says that all non-compact connected four manifolds admits a smooth structure. Yes, that's not obvious. Not obvious at all. Those are the three hard theorems you combine to get to this. Precisely. By the way, I skipped the proof of the Benka inequality completely, but I have the slides, and hopefully uh, Vikram will share the slides with you, and that has the, I think, more or less complete proof, and you can read it. It's not hard.
Okay, any more question? Maybe we can wait for 1 more minute and then end.
Sure.
So I guess this is like a very vague question, kind of,
Yeah.
but
Sure.
like, does this kind of thing generalize to even higher dimensions after like, I mean, you spoke about 3 dimensions and 4 dimensions. Does this thing generalize to higher dimensions? But because I mean, the last example that we did, that is of course very specific to 4 dimensions, because we know
Yeah.
in higher dimensions this kind of thing does not happen at all.
Precisely.
So
Yeah. No, I don't think so. I mean, Thurston-Benka inequality, I have no idea because see, it's higher contact topology works in higher dimension. Much of contact topology works in higher dimension, and sort of the kind of stuff that goes inside the proof of the Thurston-Benka inequality and the normal Benka inequality with the Seifert surface, etc. That has recently been developed. It's a very recent topic. So what goes inside the proof is something called convex surface theory. Sort of you have airplanes moving in R3, but then suppose you add an extra restriction, which is the airplane has to move on the surface of a move on a surface, and you have an embedded surface in R3. You're restricted to the surface and constrained by the plane, the contact distribution. Then what happens? That's called convex surface theory, and that has been in development for some time. It's very recent, but I don't think that you'll get an inequality like the Thurston-Benka inequality in any sense, because it's sort of really a shadow of slice-Benka inequality, and slice-Benka inequality is very specific to 4 dimensions. I mean, it's like the adjunction inequality, if you know in algebraic geometry. You have k times k plus d is equal to the is the churn class or something, right? I forget. Sorry, it's k times k plus d is equal to 2g minus 2. Yeah, that's it. For a surface inside for a complex for a scalar surface with some conditions, and a divisor inside it, d being the divisor, k times k plus d, k is the, or d times k plus d, where k is the canonical class, d is the divisor, and this is sort of reminiscent of that. And the way the proof of Slice-Bennequin inequality goes is trying to generalize it to sort of maximally generalize it to symplectic manifolds from scalar surfaces and so on. And that's extremely specific to 4D. Higher dimensional floor theory, and I don't think anyone has any clue what's there. So I don't think Benka inequality will have a sort of coherent generalization to higher dimension. It's a good question. Maybe one should explore, but I don't think so. I doubt it very much.
I see. Yeah. Thanks.
Yeah.
Are there any more questions? If there are no more questions, maybe we can wrap it up here. Thank you, Balarka, for your wonderful talk.
Thanks for inviting me. Okay, see you.